So this unit is going to deal with what we call set theory, study of sets. And at its heart, working with what we call sets and set notation, it's what I refer to as the universal language of mathematics. There's all different types of mathematics and branches. You could be an algebraist, you could be a geometrist, you could be an analyst, statistics. There's always, it's always fun to go into a math department. There's always debate on whether that is a mathematical discipline. I'm in the camp that it is, but you will find those who say it's something else. But at the end of the day, all mathematics can be written in terms of and expressed in terms of sets. And then just the way we learn and assimilate new information and organize, it truly is just, it's within sets. So as I said, I don't have my A game today. I'm still not feeling well, though I do have meds now finally. So hopefully I will be better by next week. It's a little dry, so I'm just forewarning you. But we need to get through study of notation and how we designate sets, so on and so forth. So that's what we're up to today. So let's just first define a set. And it's real simple. A set is a collection of objects. All right, so any collection of objects is going to be what we're going to call a set. The objects are called elements. So any one thing that belongs to a set is an element of the set. All right. Now there are three basic ways to designate. Or that is, describe what belongs to the set. They are one. We could just use a word description. The students who belong to the Tuesday, Thursday, 9:30, 121 class. There's a word description of a set. We could be something as simple as the counting numbers between 1 and 5. So what would belong to the set with that word description, it would be 2, 3, and 4. The numbers between the counting numbers between 1 and 5. We can use what's called a listing method. In a listing method, I actually write out the elements of the set. If it's a finite number of elements, I perhaps will just write out all the elements, but there may be, 100 elements to the set. If I can establish a pattern, I can then use ellipses to say continue on in that same fashion, but that will still be the list, what we call listing method. And then the last way, sometimes it's not practical, and we'll see an example of that here in a minute, to actually list out the elements. And even if I can establish a pattern, it may be too cumbersome to establish that pattern. And then so what we can do is write a rule basically that generates all the elements of the set. So in that idea of writing a rule that generates all the elements of the set is called set builder notation. All right. So what we're going to do is kind of kill two birds with one stone here. We're going to talk about these ways of listing or of designating a set, describing what's in a set, and tackle set notation, as well as talk about the sets of numbers that we traditionally work with in mathematics and basic mathematics in their names. So we're going to call the sets of numbers. All right, so now it is also within that ways to designate a set. You can pick up a math book and using a capital letter to designate now a set. And so for the sets of numbers, very standard for what we call the counting numbers to use a capital N. It would be bolded in a book, and you would see a double bar on the diagonal bar of the capital N. So now you don't need to memorize that or know that particularly like for the test, but that is very standard. Pick up any math book and the what we call the set of natural numbers. So we're just going to say the naturals. Now, also referred to as the counting numbers. Now, whether we're using set builder notation or a listing method, we use what we call braces. So it looks like such. And everything we put in between are going to be elements of the set. I'm just going to use a listing method. This is what we're going to call an infinite set. Now, down the line, we'll have a rigorous definition of what we mean by infinite set. But for right now, we'll just go with the idea that it goes without bound, goes on forever, never, never. So what I'm going to do is just to simply establish a pattern. Start 1, 2, 3, 4, 5, 6, 7, 8. There's no particular point you have to like stop or go to, just establish a pattern, and then we can use ellipses, continue on in that same pattern. All right, so that would be the set of natural numbers. Now the next one, I'm going to use a capital W, but that's not standard. And a lot of books, upper level type math books, you wouldn't find even this set even listed, but you will in elementary math books. And what we call the set of whole numbers. Now, the whole numbers are all the naturals, and throw in the number 0. 0, 1, 5, 6, 7, ... And that would be, again, what we refer to as a set of whole numbers. So we can already see we've got like all the naturals are in the set of wholes. So the number 5, you'd say it's natural, and it's also a whole number, belongs to both sets. The next set up the line, and this is standard, it's a capital Z, double bar like that. Probably originated, though I don't know this for sure. The German word for number is Zohlen, Zohlen. So probably where that comes from. But that aside, it represents what we call the set of integers. Now, the set of integers, I can use a listing method. it's going to be all the negative counting numbers. So I'm going to show ellipses coming from that direction. Go -3, -2, -1. So it's all the negative counting numbers and throw in the wholes. So all of those would be what we call the integers. So the number 5 would be a natural. It would also be a whole, and it would be an integer. -2 would not be a natural, would not be in the set of wholes, but it would be in the set of integers. Right. So at this point, we say, okay, what kind of numbers have we not taken into consideration? We haven't dealt with fractions. And what would that look like? Any number that can be written as a fraction belongs to this set. This is standard capital Q, and you'll usually see a double bar kind of like that. This stands for the set of what we call the rational numbers, stated rationals. Now, word description. Any number that can be written as a fraction is a rational number. If it cannot be written as a fraction, it is not a rational number. Now, here's where we run into a problem where, yeah, I could do this in a listing method type of way that I establish a pattern that would show all the possible fractions in the world. But it literally, like if we were in the classroom, I would say it would take up the entire chalkboard, like from end to end, just to do that. So it's not very concise way to do it, to say the least. So this is where set builder notation comes into play, where I'm going to write a rule that will generate all the elements of the set, in this case, all the possible fractions in the world. So you would still use a brace, looking like that. And then you put this notation in. So I'm going to use X as a variable, and then I put a bar, and I put another X. So this right here is read X such that X. X such that X. X such that X does what? This is where I put the rules. So we want a fraction. So I'm going to say A over B. So looks like a general fraction. But I got to be very specific. What is A? What is B? And so I'm going to say where. Now, this new piece of notation. Put A comma B, and then I'm going to have this kind of funky looking, looks like kind of this weird E curve like that. But this little symbol right here, what it means is element of. So meaning, so when you see this, you see two things here. We're saying they're an element of some set. So in this case, when you think about, okay, what's the most of the three sets that we have already looked at, what's the best one to pick from? Because we know we can have negative fractions as well as positive ones. So I want them to be out of the set of integers. So if rationals are any number that can be written as a fraction, I'm going to say X such an X is number A over B, where A and B are elements of the integers. But I have to, be very careful. Break any math rules. What number can you never divide by? Say that verbally or just chat it in. What number can you never divide by, ever? There's only one number you can never divide by.
Zero.
That is it. Can never divide by zero. So we'll put in a little extra rule here. B cannot equal what? Zero. All right. So but that'll do it. That would generate every possible fraction in the world just by, again, writing out a rule. So again, we're using here what is called set builder notation. All right. Now, there are still some numbers that I have not accounted for. There are numbers that cannot be written as a fraction ever. If you have a number in decimal form, basically it goes like this. If a number in decimal form, that decimal either repeats or terminates, is the way we usually express this, it can be written as a fraction. So as an example, 0.5 is what? 1/2. 0.3 repeating, so the 3 repeats forever, never, never, is 1/3. So, and technically, really, you can actually condense this down and say any number in decimal form that repeats can be written as a fraction, because even a 0.5 that we say it terminates, there's actually a repeating zero past that forever, never, never. But generally, you know, if you were in an elementary setting teaching decimals and fractions, they're about 4th, 5th grade. You're going to express it as any number in decimal form that repeats or terminates can be written as a fraction. So there are those numbers that in decimal form never repeat, never terminate. And that group, now this is not standard, I'm just throwing in a capital I, but that's not a standard thing. So this group of numbers that cannot be written as a fraction, and that is the word description there, we call the irrationals. And so I'm just simply going to say, I'm going to kind of use set builder notation. I'm going to say X such that X is a number that cannot be written as a fraction. Close. What are you doing there, buddy? Hold on one second. What are you doing? Come here. Yeah. Come on. You're right. Yeah, sorry guys. Chew on that. All right. So one more set of numbers we'll deal with here in this class. And this is standard. You see an R with a double bar. And again, in a book, it would be bolded. And it's referred to as the set of real numbers. We'll just say the reals. In the reals, we'll go X such that X is actually, let's do it this way. X such that X is an element of the rationals or the irrationals. That is, it's either basically we're, and these two sets have nothing in common, rationals and the irrationals. These are all the numbers that can be written as a fraction. These are all the numbers that cannot be written as a fraction. Basically, we throw them together in one big hat, and that's the set of reals. We can take this one step further, and if you've had college algebra, you have. And it's a set of what we call complex numbers. And that's where we have a number of the form a plus bi, where I is the square root of -1. And the reals, all the reals would belong to this set of complex numbers. But we'll stop here at this. So, when I look at this, I can say all the naturals are in the wholes, and all the wholes are in the integers, and all the integers are in the rationals, and all the rationals are in the reals. So you kind of got these guys, these poor guys are off by themselves, but then you put these two guys together and you have the real numbers. So if you take a number like 5 and say, okay, write down every set to which it belongs. It's a natural, it's a whole, it's an integer, it's a rational. I can always write 5 over 1, and it's a real. And just so we've got a few examples of irrational numbers. So I'm just going to use I there. Most famous, of course, is what? Pi. We estimated about what? Approximated about 3.14, but it literally goes on forever and ever, never repeating, never terminating. It's been carried out to billions of digits and still never repeating, never terminating. The square root of any number that is not a perfect square is irrational, cannot be written as a fraction. That is, in decimal form, it goes on forever and ever, never repeats, never terminates. Square root of 2, square root of 3, square root of 5, square root of 10. As long as it's not a perfect square, it's going to be irrational. If you've had college algebra, you have also seen this number. Anyone know what it? Give it to me as kind of like pi is 3.14. What is E? If you've had college algebra, you have seen this number. Approximated to a hundredths place. Pi is approximately 3.14. E is approximately 2.71. So, and it is a very applicable number. Everybody's heard of the Richter scale, measures earthquake intensity. It's that Richter scale is based on the number E. So how things heat up and cool down is Newton's law of heating and cooling. It is based on the number E. So if we look at business application, continuously compounding interest, that is based on the number E. So a lot of real world application. Dog, what are you doing? Sorry, guys. What are you chewing on? Yeah. Gross. All right. Any questions thus far? Anything we covered? All right. Another term I'm going to throw into here. Let's put it right here. If you hear the term disjoint sets, have no elements in common. So the rationals and the irrationals would be an example of disjoint sets. They have nothing in common. I'm not going to write this one down, but right now, two sets are equal. Say I have a set A and a set B. If all the elements are in A are in B, and all the elements of B are in A, the two sets are equal. So basically, they have the same exact elements. All right. Now, this actually kind of goes into the next section, but I need it in order for you guys to do something. I'm going to write a definition here. Stay out of there. Yes, you. All right, guys, I'm sorry. I apologize. I've got teaching remotely issues. I got a dog that's tearing and stuff. I got to put him upstairs. Come on. You're gross, dog. Come on. So I'm going to use a capital A. A set A is a subset of a set B. All right. And I've got this word, did not misspell the word if. I got IFF. IFF stands for the phrase if and only if. A set A is a subset of a set B, if and only if. And the what this phrasing means is the door swings both ways. And I'll explain it when I write the statement. If and only if all the elements of A are in the set B. So if all the elements of A are in B, then A is a subset of B. A is a subset of B. If you can, so if you show this, you get this. So the door swings both ways. It's what we call two if-then statements. If this, then this, but I can also say if this, then this. The reason I wanted to get this definition, which is actually in the next section, is I got a problem for you. And so I want everybody to, you're going to work this problem. I'm going to go ahead and tell you right now, generally, most people don't get this one right. So don't, just do your best and tell me how many ever you think. I want you to get in there. I'm going to give you a set A. It's got three elements, little a, little b, little c. And what I want you to do is I want you to write down all possible subsets of this set A. So I'll give you a start. Like you could have AB, you could have just A, so on and so forth. There's not a bunch. There's not like a whole lot of them. But I want you right now to jot down all the subsets that you can think of. And then I want you in chat, everybody, to type in how many you come up with, just the number of subsets you come up with. If we were in the classroom, I would have everybody do this, and then I would just go around and say, how many did you get? How many did you get? How many did you get? And I expect some variation here. So take a minute or two and go ahead and do that. And when you get them all that you think that there are, type in chat how many subsets you got. All right, go. I'm gonna grab a little more coffee while you're doing that. All right, well, nobody's chatted in yet, so I'm gonna go down the list here and just tell me how many you got. Michael, how many subsets did you come up with? Yep. Somebody? Okay. I'm gonna jot them down over here. Nathaniel, how many did you get? Okay. Quentin. How many did you get? All right. Chantel, how many did you get? All righty. Valentina, how many did you get? All right. Justin. Okay. Alex. Okay. Chloe. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Who am I missing? Emily. Okay. All right. So very predictably, and I use this exercise to clear up a couple different things. There's one big thing I want to get out of this, but there's another issue that, and I haven't mentioned it yet, so it's not your fault. So we'll get this fixed. And that is this. So first off, the answer is and I drew that very poorly. There are 8. So, and typically nobody ever gets 8. I can't even remember how long it's been, if it, so long that I don't remember that anybody gets this. And there are a couple different reasons why. So obviously everybody was over 8. And the reason everybody was over 8 was you're thinking about order of elements. So you're thinking like where I gave you one example of a subset of set A and B, you were thinking, okay, so the set B and A is a different set. Okay, so order that you, the order of elements does not matter. So i.e., as an example, set AB is equal to the set BA. So I alluded to it a little bit where I said, remember, a set capital A is a subset of capital B if and only if all the elements of A are in B. Didn't say anything about order. So these two sets will be equal. There's whether, however, whatever order I write the elements does not change, make them different sets. All right, does that make sense? And so that's why everybody got more than 8. All right, so if I start writing them all down, I've got A, B, got A, you can have one with just the element C, you can have one just with the element B. Could have one with BC. Could have one with AC. And by the definition we came up with here, so that's 6. You could have the set itself. So, and by definition, a set is a subset of itself. Since by definition, all the elements of A have to be in B, then a set can be a subset of itself. Now, when we come back on Tuesday, we will refine this and we'll actually talk about something we call proper subset. But we'll refine that on next Tuesday. So I came up with 7. All right. So, and again, how you were getting these numbers, you would take like BC and you're making it CB. But again, that wouldn't make it a different set. It still has the same exact elements. So the order at which I write them doesn't matter. So what could be the 8th set? And this was the big thing I really wanted to get to here. So I wanted to address order doesn't matter. And then it's an extremely important set. And like if we don't have this concept of this set I'm thinking about, we might as well go ahead and pack it up and go home. And no, we can't get rid of it. So we're not packing it up and going home. What set? It's squirrely. It's hard to think about. Trying to visualize the void is much like trying to visualize infinity. I don't know what infinity looks like. I can just express it as it goes on forever and ever and ever, but I don't know what that looks like. Much less, much the same. I don't know what the void looks like. That is nothing. What set am I thinking about? It's a squirrely one. All right, somebody answered. Yes, that is it, Mike. The empty set. All right. The set with no elements at all. And so I always refer to it as the empty set. You will also hear this expressed sometimes as the null set. I say empty set, but these are interchangeable. So empty or null. The easiest notation is a circle with a line through it like that. That represents what we call the empty set. So by default, there's no elements. So to contradict this definition, so the empty set is a subset of every set in the known universe. And that gives you your eighth. Now, when we come back on Tuesday, we're going to do this systematically to develop a formula. And then you'll clearly see, this one definitely belongs. It is one of the 8. But we'll wait to that on Tuesday. But I wanted to do this exercise to show, this is one of those subsets and to define it. So the empty set is the set with no elements, and the empty set is a subset of every set. Now, so you can use this, or you can also, I don't use this, but I know a lot of folks who have spent time in the military will make their zeros actually with a line through it. And so I always tell people, if you do that, because 0 is a number, that is an element. So if you had the set with just 0 in it, then it actually has one element in it, and that is namely 0. So you would want to use this notation. It's just 2 braces with nothing showing inside. Do not combine the 2. All right, so you'll never, as a way to just represent the empty set, don't put this inside of here. Either use this or this. If you use braces with the empty set inside, now we're talking about a concept we call power sets, and we're not going to deal with power sets right now. And those are a set of subsets. So we're not going down that road. So either use this or this. All right. So again, on Tuesday, we'll systematically develop where these come from. And then we'll clearly see this is, this has got to be one of the possible subsets. All right. See if there's anything else I want to do today. I think that is it. Any questions up to now? So for a set capital A, if you see this notation, so, and this is read N of A or cardinality of A. So this is big word, cardinality of A. So that is a fancy way to say how many elements does A have. So if you had A and it had the elements A, B, C, D, then the cardinality of A would here be 4. So There'll be a few problems where you're simply asked, you'll see that notation. So know that you're just looking for how many elements that set has.